We'll let him continue the introduction. The floor is yours.
All right. Thanks very much, Akshay. Yeah, today I'm going to be talking about signal integrity. Basically, all the stuff about PCB design that they don't teach you in EE 241 or your equivalent circuits, intro to circuits lab. Um, there's obviously a ton of stuff I won't get to today. I'll talk about some of that at the end of, if you're still interested, you want to go deeper into PCB design, PCB layout stuff, some resources to go and what to start researching if you're interested in continuing. So, who am I? I hope most of you know. I know I see some new faces around. So good that the club is continuing on. I'm Ryan, KN6REG. I graduated computer engineering last quarter, literally just like 2 months ago from Cal Poly. I was the president like 3 years ago at this point, almost 3 years ago, um, in this very fine club, and I am also a PCB layout nerd. I'm lucky enough to get to do that, not as my primary job, but as one of the things I do at work. I'm still in the office. Speaking of that, disclaimer, the contents of this presentation are mine, not my employer. Especially if anything's wrong. If there's any mistakes in here, they're mine, and mine alone. Please feel free to reach out in the chat or speak up in on voice if you have any corrections, comments, or especially questions. This is my first time giving this talk, so I'm sure that there will be some gaps. And so yeah, please feel free to ask for clarification if there's anything that you're unsure about. There are no dumb questions. And then yeah, here on the right are some boards that I've worked on. All of them vary in scope and scale. There's some more projects I probably should not show. All right, so today we're going to talk about some applications of signal integrity. So like when you're doing what with a PCB, the actual like physical copper geometry. What is a transmission line? Why do we use ground planes? What are vias and some of the things about them? And then lastly, I'll touch a bit on power routing. So when do I need to actually care about my layout? The big thing here is it is not based on your clock rate or data rate. Mostly as a CPE, I'm going to talk about digital things. But this also applies for analog. But it is based on your uh, rising or falling edge of any um, uh, clock or data signal. It's based on how fast that is, and more specifically, how long that is. So I have a little chart here of distance versus voltage of a falling, or I guess rising waveform propagating out through the transmission line, right? It's going from low to high. The wavefront is actually physically propagating down the wire. And so we see that distance here on the x-axis and voltage here on the y. And this physical length of the rising edge is what will determine if you need to take special precautions about your layout and copper geometry. In general, that is going to be about 1/10 to 1/6. If the trace length gets to about between 1/10 and 1/6 or any longer of this length, then you really need to think about all of the copper geometry, think about controlled impedance and so on. Similarly for analog, if you're doing RF, if the trace length is greater than about 1/10 to 1/6 of your wavelength, then it really starts to matter. Also, if your circuit performance depends on noise, there's, if you're designing like precision analog or audio equipment or that kind of stuff, you should probably also think about the geometry of your layout. So as I said, your trace delay or your whether or not you need to consider the copper geometry comes down to the edge length. You calculate that by first taking the speed of the signal in your whatever media it is. Most likely, it's going to be either on top of a PCB next to air or buried inside of a PCB between multiple layers of laminated fiberglass of some sort. And so to calculate this speed, I have a formula here. This is from this. A lot of the things in this presentation are referenced out of here. I have information about it at the end. Would highly recommend picking it up. Maybe not the physical copy. It's rather expensive, but it is definitely worth a read. Yeah, delay is going to be 85 picoseconds per inch divided by the square root of your dielectric constant, right? So as dielectric constant goes up, your travel or your signal is going to travel slower down the trace. And then the length of your edge is you just take this this delay factor and divide your rise time by that to get the length. So I have a small worked example here for a 40 megahertz SPI signal that's, starting to get fast, starting to get into the realm where you might need to consider this, PCB layout. Is your rise time is going to be on the order of 2 nanoseconds on the slow end, and on FR4 your dielectric constant epsilon r is about 3.5, depends on the exact blend of glue and fiberglass that they use. It can be anywhere from about 3 to 4.5. But that gives you a rising edge of about 44 inches. And remember what I said before, if your trace is about 1/10 of that, you have to start worrying about it. So maybe around 4.5-inch long trace on your board, you would have to really consider the layout, consider the the source impedance, line characteristic impedance, termination on that, and all of that sort that we're going to get into. So, that's 4.5 inches is on a PCB. That's rather long. Generally you don't want to grab a high-speed signal and pull it from one side of the board to the other. Sometimes you obviously really have to, but where you can, I guess this is one of the first things, keep any fast or critically noise critical portions of your circuit small and close together on your board. That helps a lot. So yeah, here's some applications where you do actually need to consider copper geometry, as I just touched on SPI. Other similarly similarly high-speed interfaces, I2S, RMII, USB, as I talked about before, precision audio equipment. If you don't consider your signal integrity, you can pick up buzz, hum, that kind of stuff. Anything with RF, obviously, you really need to care about your copper geometry. That's kind of the whole name of the game of microstrip devices and like microwave engineering on PCBs. Also, similarly, switching power supplies, they make very fast current transients to efficiently convert voltage up or down, and that can create tons and tons of radiated emissions and couple noise onto all of your other things nearby. So that's super common application on almost every single board, where you really need to be careful and consider it about your copper geometry. Some more extreme examples where it might, just considering and using good practices of your copper geometry might not even be enough. DDR, PCIe, JESD, some of these very, very high-speed interfaces you can try. You can kind of just guess and build and hope it works. And oftentimes that does work. But if you want to make sure you get those right, you should invest in some electromagnetic simulation software. Similarly, for like really high frequency microwave circuits, you can do it on a PCB without any kind of simulation software, but it's a lot easier with simulating it and optimizing it beforehand. So, if you're trying to build any ham radio equipment for the 10, 24, or 47 gigahertz bands, then yeah, most likely you'll be simulating that before. Transmission lines. This is for people who have not taken EE335 yet, or will never take EE335. for all my other fellow CPEs out there. So transmission line is a structure that carries a signal with certain electrical parameters. So that's going to be generally some kind of controlled series inductance and a controlled parallel capacitance to ground. So this will be distributed along your line, right? As the signal propagates down, you'll have tiny little chunks of inductance that add up, and similarly tiny little parallel chunks of capacitance to ground. So yeah, here's some various examples of transmission lines from KiCad. This is from their calculator tool. Here's a microstrip line, coplanar waveguide, coax, and a buried strip line. These are all structures, I guess, save for the coax, that are very easy to make on PCBs, and so that's why built into KiCad is a tool to help you estimate the geometry and electrical characteristics that you're going to get from certain layouts. One important bit about these is it's a very effective way to control how the fields propagate. It's, unless you have gotten deep into the way that signals actually propagate is not in the wire, right? They propagate because of the fields that are set up around the wire. And so transmission lines are a very effective way that we can control the behavior of these fields. Generally, they're going to be set up, actually not general, they will be set up between your signal and ground path, whether that's a twisted pair or it's a strip over a ground plane. Let's see, what else did I want to talk about? Oh, yes, they also provide a very, very clear return path for your ground current, right? If you just route a wire out and then, connect something to it, eventually that current is going to have to come back to whatever source is supplying it. If you feed it with a transmission line, that is a very controlled, okay, my current is going out the center and coming back on the shield. And yeah, given enough size, everything becomes a transmission line. Usually we model things this way and think about things this way once the signal propagating is on similar orders of magnitude as the size of the wave. So actually, fun fact, at grid scale, whole entire power lines do act as transmission lines at 60 hertz. All right, so what is characteristic impedance anyways? I mentioned this before. It's a fundamental characteristic of the transmission line itself. It's not equivalent to DC resistance, but it's given in the same units, so it's given in ohms. It is defined by the geometry of that same transmission line. And why do we give it, the units of ohms if it's not actually the resistance of the line, right? You take an ohm meter and stick it on two ends of a coax or of a microstrip, you're going to see almost zero ohms, maybe half ohm or less DC resistance. But say, it's it's a 50 ohm controlled line. So what does that actually mean? So from Ohm's law, that tells us resistance is equal to voltage over current. So our characteristic impedance is actually you can think about it as the current required to propagate a changing voltage down that line, right? So if we apply a 1 volt step, go from 0 volts instantaneously to 1 volt. If you've taken a signals and systems course, this might be kind of a familiar concept to you. Apply that to our line. That 1 volt is actually going to travel down the line, and the potential will go down it, charging up the magnetic field around the conductor and charging up the electric and your conductor. And the current required to set up those fields is then what defines our characteristic impedance. And as I just mentioned, the distributed capacitance and inductance of your line is also what gives us our characteristic impedance. So it's equal to the square root of L over C. All right, so that's all great. What do we actually do? What do I actually care about when I'm designing a board? Generally, you know, you just want the width. Okay, I'm just going to click my trace and lay it out. You don't actually care about when you're on the keyboard thinking about where all the fields are going. So you could first start with formulas. You could go to a physics textbook. You go to an electrical engineering textbook and calculate this by hand. It's really tedious, painful, and not super accurate. Um, so there's tools. KiCad has really cool, this free open source. If you're not using KiCad, you should get KiCad and lay out some boards. But comes with a calculator tool, and you can then go in and either analyze or synthesize the dimensions that you need to hit certain characteristic impedances that you might want for various applications, and for a bunch of different types. Similarly, ADS, the product by Keysight, it's a ton of money, but you're a student at Cal Poly, so you should get a free license while you're a student there and check it out. It has a tool called Controlled Impedance Line Designer, which actually does electromagnetic simulation of your substrate. So you can define a really complex substrate, way more advanced than what KiCads can do, and get really accurate results there. It's not perfect, but its results are going to be close but slightly different. The best way to do it is to build it and measure it. Theoretically, hopefully, your PCB manufacturer has actually already done that for you. They've built and measured a bunch of different cases and figured out what the best line thickness to draw for you is for when they actually make your board for it to produce the characteristic impedance that you want. If they don't have these tables, then you can measure that yourself. It's kind of a pain, and you need VNA and bunch of work. Yeah, for example, here below the tool calculator tool, I have an impedance constraint table. This is actually from Oshpark for their 4-layer service. So if you want to design 4-layer boards with controlled impedance, here's your line thicknesses. So for 50 ohms, you're going to want a 15 mil, so that's 0.015 inches thick trace, so decently thin trace, with signal on your outer planes, either layer 1 or 4, and then ground on your inner planes, 2 and 3. All right. So I guess this is a bit of interaction with the audience. Who can tell me where the current will flow, both on the trace and on the ground plane, and where will the electric field be? Or we have a ground plane here, and then I have transparent substrate, but you can imagine that this block here is fiberglass of some kind, and then on top we have a copper trace. Yeah, go ahead with your hand up.
So there'll be a conduction current along the length of the trace, right? And displacement current between the ground plane and the natural trace itself. But generally the field will be between the ground plane and the trace. The current will be along the length of the trace, right?
Yeah, the current will be along the length of the trace. Actually, interestingly, it'll almost exclusively be on the bottom of the trace. I drew the traces as infinitely thin here, but it'll be on the bottom side of it. And then that's, the current going out will be that way. And then interestingly, the current coming back will be constrained very, very tightly to the bottom, to the top of the ground plane directly under the trace. And yeah, as you mentioned, the resulting electric field will point down. So yeah, I have the little drawing here that shows it. We have the field line shown in green, and then the current density shown in blue below the trace. So almost all of the current on the return path, even though there's a bunch of copper all around it, will actually be constrained directly under the trace where the outgoing current is. So continuing on with this, being mindful of your return current, return current will follow the path of least inductance, at DC, that is the path of least resistance. But yeah, at higher frequencies, any kind of digital edge, that part of the signal will follow the path of least inductance, which is the path that minimizes the cross-sectional area of whatever current loop you're creating, right? So every current or every signal that has a current associated with it, and that current has to create some kind of loop, right? You can't just send signals with one wire. That doesn't really work. So the size of that loop created to return back to your sender is going to define your inductance, and that's going to define how susceptible this signal path is to harmful external interference, and also how much it will radiate. So if you stick a very fast edge signal on the example here on the right, this big loop here acts like a big inductor, and it kind of acts like an antenna, and it will just spew all out, causing you to fail emissions tests. And also, if you have other traces on this board, it will cause them to couple onto those traces. And also, any nearby harmful interference will be very, very easily coupled onto this trace as compared to the one on the left, where the current is allowed to follow directly under. So yeah, this is, I guess, important part about transmission lines is that they help you manage this return current path, and that if you accidentally break that, the results can actually be very, very, very disastrous. Resources online about signal integrity, and one of the things he says is that if you don't engineer the return path for your current for every single signal will find a return path, and if you didn't pick it out for it, it will be one that you do not like, and it will cause a lot of problems. So I guess good continuation on from transmission lines is to talk about ground planes. They're a great way to manage return current, right? If you have one plane, you can just route traces all on top of it. Oh yeah, go ahead.
Can you go back to the last slide?
Yes.
What exactly were we looking at on the right-hand side image with the little oval in the center there between the?
Oh, yeah, sorry. So this is these are two screenshots from KiCad that I took, that I annotated. So the red is our top layer copper, and blue is our bottom layer copper, right? And then so in here you can see, go ahead.
I was just gonna say, you froze for a second, so I was trying to fill the gaps where the black is where there's no ground.
Yes, yeah, the black is a cutout in the ground plane, whether you made that intentionally or accidentally. Yeah, go ahead.
So you also said return current, all the path of least inductance, that's like for AC signals, like mainly?
Yes, that's for any kind of signal, right? For a purely DC signal, that is going to be the path of least resistance. But technically, or I guess technically we could say it follows the path of least impedance. Normally the inductance is going to dominate that for any kind of signal, especially AC signals, especially digital signals. And even I'll talk about this later, even power signals, right? Any kind of changing current in your drawing from your power supply will cause voltage fluctuations. And the changing the changing current, if you have a big inductive path from your voltage supply, will cause wild voltage fluctuations at the point of current draw.
Like, do you also have to consider capacitance? Because like if the capacitance is too small, it's gonna have a large like impedance, right?
Yes. What do you mean?
Because like I see like you're considering inductance for the return current. Like is capacitance like another thing you have to think about?
Kind of. Generally the capacitance is quite useful. Right, it provides like smoothing and filtering to any kind of harmful interference here. And in this specific example, it definitely does, is helping. If you're talking about like if you have two traces next to each other, you can actually have like harmful interference capacitively jump across these. This between two traces. It's actually generally less of a problem than like inductive coupling, but it can be a big problem. They have a whole section. Okay. Yeah, go ahead.
So by the picture on the right-hand side, are you saying that the return current can choose an arbitrary path? It could either go left or right in this particular case?
No, it'll split.
It'll split even.
It'll split based on whichever one has a lower impedance. So, and I think in this picture, I drew it slightly off to the side. So the one that's shorter, slightly more of the current will go through it. But you can think about it like a resistor divider network, right? As the impedance goes up, much less of the current is going to go through that path. So most of it will go very close around the edges of your slot. And then as you get further out, less and less current dropping off very fast will be traveling through that plane.
And the idea is to minimize this path. Like,
The idea is to generally you want to minimize the loop created, right? So you can think about the one on the left in like 3D space, right? You have a trace sitting directly on top of a plane that creates a very, very thin, narrow loop. If you create a big gap in that plane, then the current has to go way around it, and then creates a quite bigger loop. Yeah, go ahead.
Not a question for this part. So like one thing I don't fully understand yet, you'll probably see why a little bit, but so say like I have a coplanar waveguide that I make with a trace, and then I put a series of vias on each side of the trace. So that essentially makes it so I can actually like kind of tune the impedance of the trace, right? But I'm also adding a lot of like inductive couple, I guess I shouldn't say couple, like a bunch of added inductive paths to ground, right? Is that, I think I'm getting the idea wrong.
So yes, when you add vias on the side of a trace, each one does have a small inductance to ground. Generally, when you have a lot of them together in parallel, that inductance gets really low. And it provides a very similar ground on the plane below and the plane next to your trace. And then, yeah, generally when you bring your plane closer, or when you do coplanar waveguide here, I think, let me go back to the picture of it. So yeah, when you do coplanar waveguide and you have your ground plane next to and also potentially below your trace, now you have more capacitance to ground, and you're going to need to make your trace thinner to compensate for that to hit the same characteristic impedance.
So partly I'm making my trace less inductive by adding more
You're-
parallel inductors because they parallel equivalence less.
You're not adding inductors to your trace. You're adding vias between the ground plane on the side of your trace and the ground plane below your trace.
I think that helps.
But in general, when you pull your ground plane really close in next to your transmission line, you're going to add another, you're basically stacking extra parallel capacitance along your trace. And that's going to drop your characteristic impedance. And so if you need to hit the same impedance, you're now going to need to make your trace thinner and more inductive to account for that extra capacitance.
Thank you.
All right, back to ground planes. So the ground planes are the lowest impedance return current structure that we can make on a board. It's basically the best possible, the cleanest possible way to take current back from signals. They also provide distributed decoupling capacitance. I guess this is similar to what you were asking Milan a bit ago. When we run traces over a ground plane, there is a distributed capacitance which can filter out a bit of like unwanted high frequency like external interference. An interesting note is ground planes don't actually have to be ground. They can be any reference voltage. Ground is generally the easiest, and you do have to be really careful when routing traces reference to another plane that is not ground, because when you take a trace that is referenced to something that's not ground, and then you via it up through to another layer where now it has to be referenced to ground instead of that other voltage, now you basically have a trace floating out without a reference and without a clear return current path. So generally, if you do run traces referenced to a different voltage that's not your system ground, you have to take a lot of care to make sure that both ends of the trace are okay with that, and make sure that you're not you're transitioning in and out of that properly. Many common mistakes in ground planes, as I talked about, gaps and slots. So you can't really run a trace through a ground plane and make just cut space around it. It will chop up your ground plane and cause a bunch of extra inductance, which creates basically susceptibility to external harmful interference, causes your trace to have more harmful emissions, slows down any kind of digital edges, right? So that'll degrade your digital signal quality. It'll worsen crosstalk, right? If you have two traces that go next to each other over a ground plane, they're going to talk a little bit, right? You can get interference jumping from one to the other. But if you have two traces that run next to each other over a slot in a ground plane, a ton of that signal is going to couple between them. And then another common mistake with ground planes is not properly transferring your return current between reference layers. So I'll get to this in a bit with vias, but when you have a trace going through a board and then you want to via down to a different layer, it was following on one ground plane, your return current was coming on one ground plane. If that other layer is not able to see that ground plane anymore, say it's a couple layers down below another ground plane, you need to provide a path for the current to flow between those two ground planes, preferably one that's really close to where your signal vias between whatever layers on your board, to minimize that loop that we talked about. All right, so how do we actually pick a layer stack up? How do we choose where we're going to put our ground planes and our signals? I have a couple common 4-layer and 6-layer stack ups here that we can look at. One option is to put signal and power routing on the outsides and ground in the middle. This is super, super common on 4-layer boards. We can also put signal on the outsides, ground and power. This has a couple advantages, but a bunch of disadvantages, so it's not super recommended. One advantage is there's a nice big distributed capacitance between your ground and power, which provides smoothing to any kind of high frequency interference on your power plane. Basically turns your whole board into a decoupling capacitor. It's very good. It's a very tiny amount of decoupling, but it has very, very low parasitics. So it's really good at actually filtering high frequency noise out of your power supply, and it makes routing power very easy. However, you can't really transition signals from the top to the bottom of the board in this case. There's no clean way to get a ground reference signal on the top layer to become a power reference signal on the bottom layer. So this method's not really as useful. If you do want to actually have a ground and power plane next to each other for this added benefit of making layout easier and adding distributed decoupling capacitance, you're probably going to want at least a 6-layer stack, which starts to get a bit more expensive. But the example I have all the way on the right, we have signal ground signal on top and then power ground signal on the bottom. So your 3 signal layers can all have easy access to a ground plane for that they can use as a reference, and then your power also is going to be everywhere on your board. So this is a very pretty common stack up as you start getting into very dense, like complex digital boards. As we can, add complexity, you'll add more layers, add more potentially different power planes if you have a bunch of different voltages floating around, more ground planes, and more signal layers. All right, so let's talk about vias for a minute. They are plated holes that you use to connect between your layers. As mentioned before, they do act like small series inductors. Each one has its own characteristic parasitic inductance. And then they also will act like a small parallel capacitance to ground. You can see this a little more clearly on the next slide, but any kind of signal via that goes next to a ground via will have, or sorry, not next, well, next to a ground via or next to a ground plane, will have some kind of capacitance to ground. Generally, this is quite small. They can also help you conduct heat through a board. So in high power board designs, something with a really big beefy FPGA or SoC, or especially with like RF amplifiers, you're going to want to pull heat out the bottom of the part, through all the vias and out the other side of the board. So you can actually heat sink very, very well through vias. Also, it's generally a good idea to have lots and lots of ground vias in parallel. It provides a low inductance ground path between all of your different ground planes on your board. And they also, interesting note, vias should be placed. It's better to place them randomly. If you place a bunch of vias in a grid pattern or any other kind of pattern on your board, you can get resonant modes on it. This is mostly applicable for RF or microwave engineering stuff, but should be avoided. It might look very nice to place them in a pretty grid across your whole board, but it performs slightly worse in some circumstances. And then also, as I mentioned before, all signal vias should be accompanied by at least one ground via next to them, if possible, if it fits into your design. This helps a lot with signal integrity, especially on long traces going across your board. If there's space, you should put a ground via next to your signal via. All right, more advanced things about vias. Couple things that we do to solve issues with them. One, via in pad. Vias are physical drills through the board. We can't actually put them that close together. And so they do take up actually a significant amount of board space. And one way to save on board space and pack more parts in is to put them inside your surface mount pads. You can't really do this without via in pad technology, because if you try to solder a part on top of your pad right here, right, if you put a surface mount part right here and put solder paste and then put your part down, when you heat the board up, a lot of the solder is going to get wicked down through the board, and your part's not going to make a good reliable connection. So what's commonly done is epoxy gets applied to the board. Some non-conductive epoxy gets pressed through all the vias and actually plugs them. And then we'll plate over the top of them so that it is a flat pad with a conductive plug below, or non-conductive plug below that, with the plated via around that. And this provides a very nice way to put vias directly in pads. This is very, very useful for BGA packages, ball grid array, where the landing pad for each of the balls on the bottom of the package, we can just place a via under and pull the signal down into the board. Also, you might be thinking, I said vias have a small series inductance. They also have small amounts, like it also forms a small stub on the part that's not used, right? So if we take a high-speed signal and bury down into the board, the rest of it will actually look like an open transmission line. And if you've taken EE335, you'll know quarter wavelength open is going to actually look like a short and cause weird issues. So you can get suckouts at certain frequencies in digital systems. That's going to result in like weird distortions and ringing in your digital noise or in your digital signals. So one common way of dealing with this is to actually back drill your vias. So on the backside of really critical high-speed signals, sometimes it's quite expensive. Go get a quote for a board with a bunch of back drilling on it, but you can actually drill out the plated via and remove the conductive material that's not needed. So I have a diagram on the right here from Sierra Circuits. They are one of the PCB manufacturers that we used when I was at Polysat. And they do have this capability. It's quite expensive. But yeah, you can do controlled depth drill to prevent this kind of ringing or otherwise unwanted stub behavior. Also, as I mentioned, vias are generally drilled through your board, right? This limits the size you can make them, especially as your board gets thick. Drilling really tiny vias gets really technically difficult, and also drilling into some materials can get very difficult. The materials can get gummy. There's lots of mechanical engineering problems, manufacturability problems. So a common technology in modern high density digital designs is microvias, where you can take lasers and burn holes through certain layers of your board during the manufacturing process and then plate those. You can get really, really tiny vias that way. And then also we can do blind and buried vias, where you have vias between layers that are not exposed at all to the outside of the board, or vias that go, from the outside in down only part of the way. Generally, these will be drilled partially through the manufacturing process and plated before the multiple layers of the board get laminated together. All right, on to the last topic, power routing. So first up for this is decoupling. Generally, you'll want to place all of your decoupling capacitors as close to the load pins as possible, and you want to place your smallest size capacitors the closest. Wherever you can, it's generally a good idea to use the smaller packages. This decreases your parasitic inductance and other package parasitics from your decoupling caps. This, one isn't always feasible because of the amount of capacitance you need. They don't make 100 microfarad capacitors that are 0402, for example, right? That's, you can't really find that. If you need that much capacitance, you will need a bigger physical size capacitor. And also you might not be able to assemble that, or it might cost too much to assemble that. You might not be able to find ones in the voltage rating you want, but wherever you can, the smaller the decoupling capacitor generally will be better. Not, obviously caveats, and every design has different decisions and trade-offs to make. Generally, you want to use larger values for more energy storage on any kind of power-hungry parts. Anything that you expect might have a lot of big voltage transients, right? So anything with really fast switching logic inside, or high-speed digital interfaces, every time that switches on and off, that's going to consume a little spike of current, and to be able to provide a stable voltage source to whatever part that is, you'll want a bigger capacitance near those ones. So also, one other extra note, be wary of resonance in your power distribution network, right? If you have all this parasitic inductance in your network, can actually form resonators with your decoupling capacitors and cause very weird behaviors at certain frequencies, which can cause like ringing and ripples in your power supply current, in your power supply voltage with changing current, right? So whatever network you've built might be more susceptible to noise and oscillation at some certain frequency than others when hit with a current spike. Also, I talked about this before a little bit. Power planes. Oh, go ahead.
Sorry, just on the last slide. So do you have decoupling capacitors on that PCB? I'm just trying to find where.
Oh, yes. Sorry. Yeah, it's a little small to see the names of um, the names of the nets. They're labeled. But this is hidden. You can't really see on the back. Is a ground plane. But there's decoupling capacitors. The power comes in at the top here. One of them is this really big thick trace here. We have one capacitor here, next smaller capacitor nearer to the part, and then the power input to the part here. This is a STM32 microprocessor here, and then I pulled the ground plane or the ground trace out, and then I could only fit one via here. There's other things on layers behind here that prevented me. It would have been nice to put a bunch of vias here and put it closer to these capacitors. But yeah, I was trying to route this across only 2 layers and having quite a difficult time with that. And similarly, there's another decoupling cap down here for this power input. And then, a couple ground vias, not as many as I would have liked to fit, but with the size, this was the best I could figure out. And then another one, we have another decoupling capacitor on this power input down here.
For the decoupling, like, are you just making sure, like, if there's any spikes in that power supply, like it doesn't, like it's just first a stable, power, stable voltage of power?
Yeah, so when we see sudden changes in the amount of current being drawn on the power supply, the voltage will fluctuate, right? So if we go to send a 1, right, we have to switch a MOSFET on from the off state to the on state, and charging up that gate to change the MOSFET state, and then to the current required then to drive that line high will cause a little tiny fluctuation. Actually, could be quite a large fluctuation, but little burst of current that now has to be consumed extra that the part was not consuming before. And then, if we have a really fast digital interface doing that couple million times a second, that can cause a bunch of fluctuations in the voltage on those lines. So yeah, you can think of these decoupling capacitors both as like filtering out this noise, but also it's essentially a way to store extra power near the part. So when the part needs that extra current for a tiny amount of time, it has somewhere close to pull it from. All right, yeah, so fan out versus power planes. I talked about this briefly on the stack up slide. But when we do a like power distribution fan out, usually you want to try to you'll do this when you have less layers available, and it's the best you can do. This is a more zoomed out example or more zoomed out picture of the example on the previous slide with the decoupling capacitors. This is a board I was recently working on. And yeah, you want to do your best to keep your tracks thicker. This isn't just to keep the DC resistance lower, but to also keep the inductance lower. So any kind of sudden current draw further out in your power network will cause less of a voltage ripple. But couple unfortunate things about this. One, it's more difficult to route. You don't get any of the decoupling benefits of power planes, and routing your signals or your power like this next to your signals allows any noise from those signals to be more easily coupled onto your power network. And also the thin traces have some kind of series inductance that'll cause ripples. Power planes, on the other hand, basically don't have any of these problems. They provide distributed capacitance, which provides a nice really small extra capacitance with very, very low parasitics that helps with really high frequency noise across your entire board. They're very easy to route, right? You just drop a power plane, you can drop vias wherever you need to pull power from. But unfortunately, they take up an entire layer or more, depending on how many voltage rails you have on one board. And they're oftentimes not feasible with digital boards less than 6 layers. maybe, like on a 4-layer board, if you only have one layer of signals and then like a layer of ground and a layer of power, you might be able to get away with running power that way. But as I talked about before on the StackUps page, and on the ground planes page, you can't really, there's not a good way to reference, or not an easy way to change the reference of a signal from a power plane to a ground plane. All right, future reading and watching. There's tons of other great resources out there, but these are the ones that I've mostly gone through in the past. One is this book here. I dropped the ISBN in this. The slides will be posted in the Discord. You can find the PDF of this online. I'm sure there's easy ways to do it. But I would actually recommend buying the book. It's worth a buy. I think I found it for about $40 something used online. And it, has been a great reference to go back to when working on designs. Also, Eric Bogatin, he's a professor at Boulder, I believe. I think. Yeah, electrical and computer engineering professor. He has a textbook called Signal and Power Integrity that is wonderful, just amazing resource. And there's a set of online lectures that go with that book that is a great resource. It's not free. I don't know how much it costs to access those lectures. I think they come with purchase of that book. But those are a great resource. But just getting started, he has a bunch of recorded interviews and presentations and stuff on YouTube about the same topics. Goes way more into depth into a bunch of more specific fields in this realm than I could in this hour-long talk. So would highly recommend looking up him and seeing some of the interviews he's done with other electrical engineer YouTubers and posted on presentations and such. So yeah, another thing inspired by this book, it always has in every chapter a bunch of points to remember out of that. So if there's a couple points I want you to remember from this presentation, it's these. One, when possible, try to use a 4 or more layer board. It really helps with your signal integrity. If you're routing any kind of moderate to high speed digital signals or analog signals, using a 4-layer board with signals on the outside and ground on the inside is, tried and tested way of significantly improving your signal integrity performance. Place your decoupling capacitors as close as possible to your device. I can't tell you how many times I've seen electrical engineers at this school just like place their capacitors somewhere on the other side of the board. Place them as close as you feasibly can. That helps a ton. Keep all of your critical fast edge traces as short as possible, as we talked about before. Once you get to about 1/6 to 1/10 of the length, your trace length is 1/6 to 1/10 the length of your rising edge or the wavelength of your analog signal that you're dealing with. You really need to start thinking about signal integrity. So the shorter you can keep them, the less you need to think about all of these other concepts. Think about a return current for all of your signals. Bogatin says if you don't plan a return path, the circuit will find one and you won't like it. It'll cause all sorts of headaches, failed EMI compliance tests, bad signal integrity, all of the above. I guess tacked onto this is place 1 to 2 ground vias adjacent to each signal via wherever you can, wherever possible, wherever you're switching a signal from one layer to another, and it no longer has access to that same ground plane. For controlled impedance, follow the PCB manufacturer's guidance. Oftentimes they'll tell you what to do. I'm most familiar with Park, but a bunch of other like quick turn fabs will tell you exactly how wide to make your traces to meet certain common impedance specifications for their process. So follow that. They're usually almost always going to be more correct than any kind of simulation or calculator tool that you plug it into. Generally, these are based on like actual measurements from their exact process. And then I guess kind of in a similar vein to, measurements are always more important than what you can simulate. So simulate what you can, what you can't, just build and test it. Generally, especially for a lot of these like signal integrity type things, it is going to work, just maybe not well. If you want it to work well, obviously you need to think about all these things and design around it. But the best way is to actually just build, test, try it out. All right, questions. I see a couple in the chat from Nick that I will answer first and then open up to the room. What free and open source simulation programs are out there? I've heard of OpenEMS, but don't know anything about it. Does it integrate with or import PCB designs from KiCad? Yes, it does. It's a ginormous pain in the butt to use. It's poorly supported, poorly documented. I believe it's a MATLAB and Python library, or MATLAB and or Python or Octave library. There is a way to export KiCad layouts into FreeCAD and then take the steps from those, transform, assign like copper and other materials, your dielectric materials to the exported 3D model of your board, and then run simulation on that. I've never gotten it to work. I've dumped probably at least 20 or 30, 40 hours of work into that over the last 2.5 years, on and off trying to get that set up and working. If you can, please send me resources on how to do it. I've just run into like library hell on Linux, and just trying to get it to actually work. Depends on old versions of Octave that I can't install on the version of Fedora that I'm on, and yeah, it's technically possible. Beyond that, there's one called Quux, but I think it mostly just does like ideal transmission line sim and SPICE integration. You can look into it. There's a non-open source version of it. It's still free though, called Quux something. That's more powerful, but it runs only on Windows. I don't know. There aren't too many great options in the free and open source world for EM simulation. Open EMS is basically your only bet, and it's a bad bet. Hopefully in the future it can get better, but that's just not where we are right now. For KiCad itself, are there any plugins or built-in tools that help with high-speed signals? You mentioned transmission line tool, but what about for differential pairs? Yeah, so KiCad, I didn't touch on this in my presentation about diff pair routing, but yeah, KiCad has tools to assign net classes to various traces, which you can define the width of single-ended traces and the width and spacing of differential pairs. And then it also has tools that tell you what the length is. So if you have like a bus with multiple diff pairs, you can adjust the skew within each pair and the skew across all of them. Your whatever application you're doing has some kind of application note, which will tell you approximately how bad or how much like signal skew can you tolerate, and you can take that, put that into KiCad, and it will tell you whether or not you're meeting the constraints you give it. It's actually very, very nice. I've done this on a couple of my boards. Do you recommend separating, isolating ground and other planes between digital and analog domains? No. This is a commonly debated thing. No, it is generally very treacherous waters to have multiple or split ground planes. Usually you're going to have a much easier time getting things to work well if you just have a single ground plane. This is the wisdom of any engineer I've talked to here at Keysight. But I've seen a bunch of contradicting information on the internet, and my experience would tell me that is wrong. You can build it and test it, but no, generally you want one continuous, as good as possible ground plane. But yeah, there's lots of weirdness and standards and safety compliance stuff and such. You can go down the rabbit hole with grounding and ground planes. What is the biggest PCB stack up you've worked with? Some of the boards at work I work with are 26 layers. I don't think I've worked with anything more than that. Let's see, via and pad, is that a tinted via? I think tinted via is generally when they put solder mask over the via. Via and pad, they push non-conductive epoxy fill through the vias and then do another plating round on top of the via. Decoupling, what about multiple capacitors with different values? Generally, that's okay. You want when you have different size or different value capacitors, it generally matters less than the actual physical size of the capacitor due to the parasitics. So you do still want the smallest physical size closer. A lot of wisdom will tell you, various app notes and such you read will tell you want to stagger your various sizes to deal with different frequency ranges. I've also heard that that's sometimes not a great idea and can lead to extra ripples and other instability in your decoupling network. The best way to figure that out is, obviously test it, measure it. Beyond that, you can simulate it. But I've seen very, very convincing results that say it is not necessary, and a lot of times it is best to just have physically small capacitors of similar or equal value, all very close to your part. The smallest is what should be the closest. All right. Any questions from the room? Yes, go ahead.
I think at least from the slide that showed the Oshpark impedance, like trace widths, did it mention anything about length, or is that even important?
It did not mention anything about length. Length is sometimes important, depends. If you're doing RF stuff, oftentimes you do care about quarter wavelength, right? You need to match your length to the signals you're putting down it, right? Maybe you want to do a quarter wave impedance transformer, or you're trying to build Wilkinson splitters or branch line couplers or whatever else. Yeah, to do that, generally you're going to want to simulate or plug that into some kind of calculator. ADS has tools for that. KiCad's line calc has tools for that. It'll calculate, based on the length and the dielectric constant, right? How the speed of propagation slows down, and then what lengths correspond to what frequencies and what wavelength. Yeah, basically what wavelength corresponds to what frequency. Yeah, go ahead, Akshay. Or is it a follow-up to the same question?
No.
Oh, okay. Sorry. Then sorry, I don't know your name on the right.
Wait, on the right. So
This-
you get LJ. But so you finish writing all the traces on your board, you run it through some simulations, you get it manufactured, it comes back to you, and it doesn't work. What is your sort of strategy, and kind of how do you go about debugging your issues, and seeing exactly what's wrong? What's sort of the method or the strategy that you apply? What are the steps?
So I guess it depends what goes wrong. And I would be very, very surprised if you went through, you considered all of these things while designing it, did a simulation, the simulations look good, and then your board just completely doesn't work, right? If there's some crazy failure, you're generally going to catch that in simulation, especially if you have an expensive simulation package, and it's all, well set up and correctly run. But, assuming maybe you don't have access to that, maybe, there's something the sim didn't actually catch. Depends what the failure mode is. If you're getting, tons of radiated emissions, then you're going to want to track down where that's coming from. Often that should be pretty obvious by inspecting your design, looking for, discontinuities and such. You can, if you do need to track something down like that, they make near field probes, and you can look at the electric field around the board. You'll take your little wand and poke it near the board and connect that to an oscilloscope and see what the E field looks like around the board and go, looking that way. If you're having just like link issues, like say like some kind of digital interface, you're getting a lot of like packet loss or error on it. A common tool to look at that is eye diagrams. So you can place an oscilloscope probe on the trace and look at the like over time long-term statistics of what path does the voltage follow over time. And so you can look at and see, okay, is my receiver actually receiving something that, looks like a kind of a square wave or whatever waveform you expect to see on the receiving end. For power supplies, like power distribution networks, similar, you're going to take an oscilloscope probe and probe at the point of your loads and look at, okay, what is an acceptable amount of noise on my power supply trace? What kind of noise profile, like versus frequency, is it allowed to look like? Those kind of things. Some of them you'll have standards for, some of them you'll have to look in the data sheet for whatever loads. Other ones, could be defined by your product. Milan, go ahead.
Yeah, sorry, I was just gonna ask about the decoupling capacitors, like choosing the value, like the capacitance you want for those. Like what I was thinking was like you just want them like to be like a large value because you want them to store like a lot of like energy to protect against
Yes. Yes, but like with big asterisks next to it. Generally, you want them to be as big. Well, you want them to be as big as you need them to be, and you want them generally the bigger the better. Bigger in capacitance, smaller in physical size. The two things do contradict each other. So oftentimes you want to look to the data sheet of whatever kind of device you're looking at for guidance. So like in the STM32 example I gave, ST gives you in their data sheet the recommended decoupling network. I think that's like a 10 or 100 nanofarad capacitor on each voltage supply pin plus a 1 microfarad on the whole package, or a 10 microfarad on the whole package, something like that. It'll be, usually on the order of 10 microfarads, 1 microfarad, or maybe 0.1 or 100 nanofarads on like per pin on a multi-pin device. More oftentimes doesn't hurt. It adds more price. But yeah, generally, most of the devices that you're using in the data sheet tell you. And if you follow that, you're generally good. Akshay, go ahead.
Is there any advantage in mixing and matching via sizes, or do you just like choose the smallest and pack as many as you can?
Your manufacturer will hate you if you choose the smallest and pack as many as you can. Generally, I mean, yeah, a lot of quick turn manufacturers might actually charge you extra if you use too many vias. If you're working with a board fab, they will have their engineers that will talk to you about your design. Yeah, I don't have much more guidance on that. I usually just stick to one via size. That's pretty common, but I know you can use other, sometimes there's a small assortment of via sizes that you get used on a board.
Hey, Brian, this is Dennis. Really great talk. I really enjoyed it, and really great insight. Thank you.
Oh, thanks, Derrickson. All right, Milan, go ahead.
Just and for the decoupling capacitor, like when you say like put it close to your device, I mean like what is I'm just trying to think like close to the device, like all like just packed like together, or
yeah, as close as you possibly, like right next to it, or sometimes it's pretty common on really dense boards to put them on the other side directly below the part they're decoupling, right? Especially for like BGA packages, you're already having of one via for every ball especially all the balls in the middle of the package. A lot of those are going to be power supply pins, and you can just drop capacitors directly on the backside of those vias.
And sorry, you might have said why, like, we have to do that. Could you explain again, like, why it has to be closer to the device to decoupling?
A couple reasons. The biggest one is you don't want the series inductance of the power supply trace between the capacitor and the device that's taking this current. Also, you don't want any extra trace length, like as I talked about before, any kind of voltage. The higher frequency you go, the more distance, I guess, yeah, the less distance that this voltage fluctuation actually physically occupies, right? So at higher frequencies, there can be more difference in amplitude over the same distance. And so if you're trying to get rid of these high frequency like components, you're trying to short those to ground essentially through the capacitor. Right, the capacitor presents a very low impedance, series impedance as frequency goes up, right? The exact opposite of inductors. And so you want that to be as close to the same physical node, right? As you're trying to actually short from, right? Because if you're like, you can imagine it like you're pinching off the voltage at that frequency at that point. If you're supplying something way over here, there can still be ripples at that frequency over here, right? So you want to bring those as close together as possible as one. Two, it decreases the inductance of that trace. And also you can think of it like you're trying to store the energy as close to where you're going to use it as possible. Yes, go ahead.
So for your clock signals, do you apply any kind of like pole shaping for like really higher frequency sort of, or like high speed electronics? Or is that kind of a no-no?
I'm sorry, you cut out.
You apply, so for your clock signal, do you apply any kind of pole shaping to like kind of minimize like frequency content in general, like along that?
It depends. Sometimes you want a very nice square edge clock signal with lots of really high frequency components. Okay, and the speed of that edge is going to determine what the highest frequency components are that you need to be worried about. Then that's fine. In some applications, you do really need that edge, and sometimes you don't. Sometimes you just need a reference signal and not a digital clock that you're trying to decide bits based on.
I imagine like the only case, well, I guess, and really where you would, that's like an absolutely, maybe like necessary is if you're doing some kind of like amplitude triggering as opposed to like edge triggering too, but I don't think most circuits really work on that.
I mean, sometimes they do. Some like clock receivers will have like comparators in them to produce a cleaner square wave. Sometimes some like advanced receivers will have their own clock that they generate, and they'll lock a PLL to the reference clock. Right, there's lots of really advanced stuff that you get into when you talk about like high-speed digital clocks. Oftentimes they will be at those very, very high data rates. Even as much as you're trying to make it look like a square wave, it will very much look like a sine wave.
Thank you.
All right, any other questions? Cool. All right, I think that's it. Yeah, you can find me on Discord. I'm on the CPark server. Feel free to shoot me a message in any of the channels, or you can find my non-student email here. I'll have access to this for quite some time in the future. So yeah, feel free to shoot me an email there. Yeah, thank you all very much for coming to the presentation tonight.
Thank you, Ryan.